This is a $100 bill. You've touched one, spent one, maybe folded one into your pocket without a second thought. But here's what almost nobody realizes. What you're holding isn't just some paper. In fact, isn't paper at all. And the moment you understand what it actually is and what it takes to make one, you'll never look at cash the same way again. Every single dollar bill in circulation is the result of a process so precise, so layered, so deliberately difficult to replicate that even the world's most advanced printing equipment can't even come close to copying it. Not because of the design, not because of the ink, because of what happens before a single drop of ink ever touches it. The Bureau of Engraving and Printing produces over $100 billion worth of currency every single year. Every decision made in this building exists for one reason: to make copying it physically impossible. And that starts with something no counterfeiter can buy. Most people assume a dollar bill is made of paper. It isn't. Actually, it is 75% cotton, 25% linen. Cotton fibers are longer, stronger, and behave completely different than wood pulp under pressure, under water, under years of daily use. A $1 bill survives roughly 6 years in circulation. A $100 bill, over 20. Normal paper disintegrates. This material doesn't. But that's just the foundation. There is exactly one company in the United States authorized to produce this material: Crane Currency. They've supplied the US government since 1879. But Crane doesn't just manufacture a durable fabric to carry the design. It creates the first security feature. Before any press runs, before any design is applied, the substrate already contains 3 embedded security elements: colored security fibers, red and blue threads distributed randomly throughout the material. Not printed, not applied, woven in. Their distribution can't be reproduced consistently, which means no scanner, no printer, no copier can replicate the pattern. A security thread, a narrow polyester strip physically embedded in the paper during production. It runs vertically through the note in a position specific to each denomination. It cannot be removed without destroying the bill. And a watermark, not printed but formed by variations in the material's own density. Hold the bill to the light. You're not seeing ink. You're seeing the structure of the material itself. A blank sheet of this material, no ink, no design, no serial number, is already a federal crime to possess without authorization. All of that, and the material is still just a blank sheet. What gets embedded into it next is the reason most counterfeiters don't even make it to the press. Because this next security feature is a genius thread. In normal light, it's nearly invisible. Hold it to a light source, it becomes a clear, readable strip. Under UV light, it glows. And the position and color of the thread changes by denomination. It sits in a different location on a $5 versus a $20 versus a $100. This is why one of the oldest counterfeiting tricks, bleaching a $1 bill and reprinting it as a $100 bill, fails immediately. The thread is already in the wrong place. No amount of skill fixes that. The material doesn't just make the bill durable, it makes the bill identifiable. And still, no ink has touched it. What most people call the design of a dollar bill is not a design. It's an engineering document. The portrait of Benjamin Franklin on the $100 bill is not a photograph. It's not a digital illustration. It's a hand-engraved image, created by a specialist using a combination of traditional steel engraving tools and digital assistance, carving thousands of individual lines into a steel die by hand. Those lines are extraordinarily fine. Their depth, spacing, and direction determine how ink sits on the final surface. What creates the sense of dimension, the slight three-dimensionality you can feel when you run your thumb across the portrait. The engraving is then transferred from the master die to a production plate. That plate is cleaned, polished, and chrome-plated. Chromium makes it resistant to the enormous pressure it will face. Thousands of prints before any degradation. This isn't drawn. It's manufactured to a tolerance measured in fractions of a millimeter. That's the foundation. Months of material engineering compressed into a single sheet. And now, for the first time, it meets the press. The first press in the sequence is an offset press, 15 meters long, 70 tons. It runs at up to 10,000 sheets per hour, laying down the background layer, the complex color fields that form the visual foundation of the note. These aren't decorative. They serve a specific function. The layered color patterns create a visual fingerprint that standard scanners and photocopiers cannot accurately reproduce. Try to scan a bill and print it. The background will smear, blur, and fail to replicate. Every 500 sheets, a human inspector pulls a sample. Manual review every single time, alongside continuous digital monitoring. That's the first layer. Now comes the process that makes counterfeiting physically, not just legally, impossible. Intaglio printing. The engraved plate is inked. Then every trace of ink is wiped from the surface, leaving ink only in the recessed grooves of the engraving. The sheet is then pressed against the plate at up to 20 tons of pressure. Not printed onto, pressed into. The paper is literally forced down into the grooves. It picks up the ink from inside the plate, and when it releases, the ink isn't flat, it stands up from the surface, slightly, microscopically, but physically raised. Run your fingernail across the portrait on a $100 bill. You can feel it. No normal printer can do this. Intaglio printing is not a technical limitation that's hard to overcome. It's a physical process that requires a machine the size of a room and the weight of a tank. After intaglio, the sheets don't move. They sit for 72 hours. The ink is thick, far thicker than standard printing ink, and it needs time to cure completely. Move the sheet too early and the surface smears. While this is happening, there can be up to $300 million worth of printed currency sitting in the production facility at any given moment. It physically exists now, but it isn't money yet. At this point, the sheet has survived every press, every layer, every weight, and it can still be destroyed by a flaw you'd never see with the naked eye. The offline currency inspection system scans every sheet, both sides, at up to 4 million pixels per sheet. It runs at 2.5 sheets per second. It detects color deviations, misalignments, microscopic surface damage, ink inconsistencies, things no human eye catches at production speed. Any sheet that fails is pulled. There is no tolerance, no acceptable margin of error. The standard is absolute. If a note isn't perfect, it doesn't exist. In the final print pass, each note receives its serial number. This is the moment it becomes a unique object. The serial number encodes the Federal Reserve Bank of origin, the series year, and an individual sequence, making every single note traceable, distinguishable, and unrepeatable. No two notes share a serial number. Then, the sheets are cut. The moment, the large printed sheets become individual banknotes. Somewhere in a building in Washington, D.C. or Fort Worth, Texas, a blade descends, and currency is born. From there, the notes are counted, bundled, and stacked. They're shrink-wrapped, labeled, and moved to vaults. Then to Federal Reserve banks. Then to your wallet. Up to 2/3 of all $100 bills in circulation are held outside the United States. Not because the U.S. exports them, because people in unstable economies, in countries with collapsing currencies, in markets where trust in local institutions has broken down, they choose to hold U.S. dollars. A new $100 bill design takes over a decade to develop. It has to work in vending machines in Tokyo, in market stalls in Lagos, in bank counters in Buenos Aires. It has to survive hands, humidity, salt water, washing machines, and it has to fail, visibly, immediately, unmistakably, the moment anyone tries to copy it.